Hello, everyone. Wanted to make a quick video for you to help you with some of the problems in section 5.2 that we did not get a chance to um, work through. And I had this all pulled up, and then I got kicked out. So let's try it again. This one. 5.2. There we go. So we worked through section 5.2 in class, but there were a few on these last page that we didn't get to. So I wanted to kind of work through them so you had them to work with. So I'm going to start here with this number 2. All right, so we have some information here. Given that the integral from -2 to 1 of f of x dx equals 3. Okay, let's think about what this means. I've got some function f. I don't know what it is, but I know that the area underneath it from -2 to 1 gives me 3. Okay, and I know that the integral from 1 to 4 of f of x dx is -2. So that means the area underneath f of x from x equals 1 to x equals 4 is -2. So I've got f of x here. I don't know what it looks like, but I know that from -2, right, x equals -2 is over here to 1. I know that this area is 3. And I know that from 1 to 4, say from 1 to 4, this area over here is -2. Now I realize it's kind of weird. That's negative area. What that means is that I've got some area underneath the x-axis. So this picture is not perfect, obviously, because all of that area is pictured as above the x-axis. But that's going to help us just kind of picture what this looks like, even though it's not perfect. So, all right, so that's on f of x. And then I also have this other function over here, g of x. This is a completely different function. I don't know what it looks like, right? It can be up above and down below. But from -2 to 4, here on g, let's say all of this area together, all of this area is 9. Again, I don't know what it looks like. I'm just making stuff up. But this is on g of x. And this function over here is on f of x. And this is the information that I know about these functions. I know something about area. Okay, and I am asked to calculate the value of this guy. The integral from 4 to -2 of f of x minus 3 times g of x dx. So I need to find the area under f of x minus 3 times g of x, whatever that function looks like. I have to find the area under it starting at x equals 4 and ending at x equals -2. Okay, so this is kind of one of the weirdos. I've got a bigger number on the bottom than on the top. This is going backwards. This is going from 4 back to -2. And so that's gonna make this harder for my brain. So I'm gonna use one of our rules up here. It's this guy. If our bounds of integration are backwards and I've got a bigger bound on the bottom, what that's going to do is it's going to be the negative of the integral going forwards from a smaller to a bigger. And basically that's just because when we do our area calculation, our b minus a becomes negative. But for us, really, it just means that I want to flip these bounds so that they're in the right order so that my brain doesn't freak out and I can process this a little bit better. But to flip that the right way, it's going to make all of this negative. So I'm going to have to make sure that I multiply all of this by -1 when I'm done. Okay, now to figure this out, I don't know what this whole function looks like, but I know what the pieces look like. I've got information about f of x and g of x separately. So we want to separate this into two integrals. So it's going to be the negative of all of this, and I'm going to separate this into two integrals. The integral from negative 2 to 4 of f of x dx minus the integral from negative 2 to 4 of 3 times g of x dx. Right, I can split that up into two pieces. And because this is 3 times g of x, I've got a number times a function. We've kind of talked about this a little bit. I can take this 3 and actually pull it out of the integral. So I'm going to go ahead and I'm just going to kind of take that out, and I'm going to put it out here. I'm just going to pull it out because I can do that. Again, the thing that allows us to do that, I'm using these two ideas together. We split this up into two separate integrals, and if there's a number, I can pull it out of the integral. Okay, so I can separate this like this. And now I just have to figure out what each of these pieces are. Okay, so how about, let's start with this guy. The integral from negative 2 to 4 of f of x dx. This is the area under f from negative 2 to 4. Well, guys, I don't have the integral from negative 2 to 4. I have the integral from negative 2 to 1 of f, and I have the integral from 1 to 4 of f, but I don't have the integral from negative 2 to 4 of f. I only have negative 2 to 4 of g. So how am I going to do this one? How am I going to figure out what the area under f from negative 2 to 4 is? Well, I'm just going to add the two areas that I have. This one is the area from negative 2 to 1, and this is the area from 1 to 4. If I add those two together, I'll get the total area from negative 2 to 4. So I'm going to make this 3 plus negative 2. That's going to be the area here from negative 2 to 4, right? If I add these two pieces together, that's the total area. And then I'm going to subtract from that 3 times this integral, the integral from negative 2 to 4 of g of x dx. Well, that's the area underneath g of x from negative 2 to 4. Oh, and I have that right here. I don't really have to change anything. From negative 2 to 4 of g of x dx, that area is 9. So I have all of those pieces, and now I can just kind of put it together. Let's see, 3 plus negative 2, that's 1. 3 times 9 is negative 27. And so 1 minus 27 is negative 26, which makes this whole thing a positive 26. So I have 26 units of area underneath this function, f of x minus 3 times g of x, from x equals 4 to negative 2. So you just kind of have to work with what you have and figure out how to get what you need from what you have. Sometimes you're going to have to put pieces together like these two. We put them together to get this guy. Sometimes you might have to subtract them. Sometimes we'll only need the area from 1 to 2, but we'll have the area from 1 to 4 and from 1 to 2. And then so we could subtract the area from 1 to 2 away from the area from 1 to 4, and we would just be left with the area from 2 to 4. So you're going to have to kind of play with areas sometimes. And if you're having a really hard time, I think these pictures and drawing, okay, where is this area? It doesn't have to be perfect, right? Like here, my graph was above the x-axis with a negative area. It doesn't have to be perfect, but it can help you picture where these pieces go so you can figure out if you're adding them or subtracting them. Okay, we did this one in class. Again, you're just graphing y equals the sine of x. This is a back pocket function. You know what this looks like. From 0 to 2 pi. And we're finding the area from 0 to 2 pi. So we're going right from here all the way to here. All of the area trapped between that curve and the x-axis. This should be perfectly symmetric. So using your imagination and pretending that's perfectly symmetric, we get 0 units of area out there because the positive area here plus the same area but negative down here is going to cancel each other out. Okay, let's try this next one, B. I want the area from -4 to 2 of 2x plus 4 dx. Okay, what area is this asking me to find? Well, I want the area underneath y equals 2x plus 4. So I want the area underneath that function, or trapped between that function and the x-axis, from x equals -4, 1, 2, 3, -4, all the way up to 2, 1, 2. Okay, well, to figure out what that area looks like, I have to figure out what this function looks like. Y equals 2x plus 4. This is a line, right? Y equals mx plus b. And I have a slope of 2 and a y-intercept of 4. Okay. And I think this is going to be a little low, so I'm actually going to move this a little bit. So y equals 2x plus 4. I'm going to put it down here because I think I'm going to have to make this taller. So 1, 2, 3, 4. Here's my y-intercept. And I have a slope of 2. So I'm going to rise 2, run 1, and rise 2 and run 1, and draw my line. Okay. This isn't perfect. I think that's actually going to go through that point. Sorry, it's not perfect because I'm a human being and it's just not going to be perfect. Okay. But hopefully you can use your imagination. We have a nice line there, right? It's lovely. Okay, and I need the area trapped between this line and the x-axis from x equals -4 to x equals 2. So the area trapped between this line and the x-axis. Well, from -4, I'm going to get area in here, right? That's my first piece of area. And then I'm also going to get area over here on this side. When I cut this here, I'm going to have area underneath here. So that's the area, the shaded red, that I'm trying to find. So really, I've got a couple of triangles. Well, the area of a triangle is 1/2 base times height. So now we can just figure out what are the base and the height of each of these triangles is and find the area. Okay, so how long is my base over here? Well, I go from -4 to -2, so that's 2 units long. And then how long is this one? Well, I go from -2 to 2, so that's 1, 2, 3, 4 units. Okay, and now I just need to find the heights of each of these. So let's start with this one down here. How would we know how big that is? Because as you know, my graph is not perfect. And so I can't just look at this and eyeball this and say, "Ooh, I don't know what that is." How would I know how far down that goes? Well, this x value is -4, right? That's where we start. This is the y value on my function at x equals -4. My function is right here. I could actually plug it in. Y equals 2 times -4 plus 4, and that'll tell me what the y value is down here. That will tell me what this number is. So I'm going to have -8 plus 4. So my y value here is -4. That's my y value here, which means the length of this side over here is 4. And what your brain likes is totally up to you. My brain likes to keep the lengths positive, so I like to put a 4 in there. But if you want to put a -4 here, because technically I'm below the x-axis and my y value is going to be negative there, and that's going to make the whole area negative, you can either make this negative and work with that, um, or you can keep it negative as you do your calculations and then just remember to make the whole area negative. It's really up to you and what your brain likes. All right, so now we need to find the height over here. To find the height over here, I'm going to take x equals 2 and plug it into my function. So I'm going to get y equals 2 times 2 plus 4. That means this y value is going, sorry, that's a 4 plus 4. My brain's trying to do the math before I write it down. So we're going to have 4 plus another 4. This height is going to be 8. Okay, and so now to calculate this area, I'm going to have this little triangle down here, which is going to have negative area. So I'm going to have -1/2 my base, which is 2, times my height, which is 4. And again, I just put my negative out front and say this is going to have negative area because it's below the x-axis. But you can also just make this 4 negative and say 1/2 times 2 times -4. It's what your brain likes. And then plus the area of this triangle over here. This is all positive area, so it's going to be plus a positive 1/2 our base, which is 4, times our height, which is 8. And now we just have to do the calculations. So these 1/2 times 2 is just 1. They're going to cancel. And so I'm going to have -4 plus 1/2 times 4. That's going to be 2 times 8. That's going to give me 16. -4 plus a positive 16 is going to give me a positive 12. That is going to be the net area or the signed area that comes out of this integral. Cool. So we're drawing pictures here and we are using geometry to help us with this. All right, so now we're going to do this one. All right, so what is this area? What is this? What area does this represent? Let's try that. Yeah, it's going to be the area from x equals 0 to x equals 6 is over here. Underneath the function y equals the square root of 36 minus x squared. What does that look like? It's probably been a while since you've seen something like this. Okay, well, I don't really know what that looks like. So let's think about this a different way. I'm going to kind of work on the side here. And sorry, I've got stuff like everywhere. Okay, so y equals the square root of 36 minus x squared. To figure out what this looks like, I'm going to square both sides. And when I do that, I get y squared equals 36 minus x squared because the square and the square root cancel each other out. So I just have 36 minus x squared. Add that x squared to both sides. And what this looks like is going to be part of x squared plus y squared equals 36. Now, what does that look like? It's actually a circle. If you will recall from geometry forever ago, x squared plus y squared equals r squared is the equation of a circle centered at the origin with a radius of r. So this is actually a circle centered at the origin with a radius of, well, let's see, 36 is r squared. So since 36 equals r squared, I'm going to take the square root of both sides. That means r is 6, right? My radius is 6. Okay, so this is a circle with radius 6. Actually, I'm going to move this over here because we're going to want that space. So I have a circle of radius 6. Now, the interesting thing about this is because we had to square both sides, technically this function represents the whole circle. X squared plus y squared equals 36 is the entire circle. Because we had to write this as a function, to represent this as a function, we separate this into two separate pieces. This piece at the top, this is really the positive square root. So that would be represented by the positive square root of 36 minus x squared. And technically, to represent this bottom part, that would be the negative square root of 36 minus x squared. So the thing that we had in here wasn't actually the entire circle. It's just this top half above the x-axis where it's the where it's the positive square root. So I'm going to come back over here. And so really what this thing looks like is it's the top half of a circle. And again, I'm a human being, so use your imagination for me and pretend that this is a perfect semicircle with radius of 6. And it's the top half. So this is actually what this function looks like. It's the top half of a circle. Okay, so now that we have that drawn, what area are we being asked to find here? It's the area trapped between that semicircle and the x-axis from x equals 0 to x equals 6. I only want the area from 0 to 6, and it's going to be the part trapped between the semicircle and the x-axis. So it's just going to be this section right here. It's a quarter of a circle with radius 6. So how would I find the area of a quarter of a circle of radius 6? Well, it's going to be a quarter of the area of a circle with radius 6. The area of a circle with radius 6, you could go back to your geometry sheet from 3.10 forever ago, and you would find that it is pi r squared is the area of a circle. We only need a quarter of that, so we're going to multiply by 1/4. We're going to plug our radius of 6 in. And this is going to be 1/4 times pi times 36. 36 times 1/4 is 9. This is 9 pi. That is the area of this glorious quarter of a circle here. Cool. Again, so just draw these and find your area, shade it, use your bounds, and then look to your geometry formulas to help you. And just be careful and remember how to graph some of these guys. Okay. Now, what would absolute value bars do? What would that give us? So your homework asks you to work with some things with absolute value bars. So let's just say I had the integral, oops, this turned off. If I had the integral of the absolute value of f of x dx from a to b. So I wanted the area underneath the absolute value of f of x. What would an absolute value do? Well, what does an absolute value function do? It makes everything positive, right? Because technically it's distance from 0. It takes any value, keeps the value the same, but makes it positive. And so what would an absolute value do for area? it would make all of our areas positive. So if we came back up here, say, let's just look at this guy real quick. The integral from -4 to 2 of 2x plus 4 dx. If I put absolute value bars around that, and if I did the absolute value of 2x plus 4 dx from -4 to 2. If I add absolute value bars to this problem that we did up here, that absolute value would basically take all of our y values and make them positive. And for our integral here, it's going to take all of our area and make it positive. So we already have a picture over here, which is why I wanted to do this one, so you can kind of see what an absolute value does fairly quickly. So this absolute value would take all of this area and make it positive. And this area up here is already positive. We did that. We got 1/2 times 4 times 8. That had a positive area of 16. And then it would also take the area of this triangle down here, but it would make it positive. So instead of this triangle having an area of -4, the absolute value would make that triangle have an area of, yeah, +4. So if I put an absolute value in here, this one would give me an area of 20. Absolute value bars make your function and thus the area positive everywhere. So we're going to use absolute values to calculate, to basically force our integrals to count all area as positive. And so I want you to think about that a little bit and play with some things in your homework to try to figure out how to use those absolute value bars. And then we're going to work these two in class next week together because I want you to have a better idea of how to do those. But for now, I want you to leave you with the idea that absolute value bars are going to make all of our area count as positive. So use that, go forth, work on that 5-2 homework, and I will see you next week. Have a lovely weekend.